Welcome back, Marauders. This video is 6.3 line spectra and the Bohr model. In this video, we're going to take a look at the line spectra, mainly from hydrogen, but from any element, and how that's used as evidence for the Bohr model. So the Bohr model was a more advanced model. It starts to explain how the electrons could be arranged around an atom. Most of you have probably seen the Bohr model before. So you have the nucleus, and then you have these various orbits around the nucleus where the electron can be found. So the electron could be found on this orbit, or this one, or this one. And you guys have probably seen that in your earlier science classes. And so what evidence do we have for this model? How did Bohr come up with this? Well, in the last section, we looked at these two equations. The speed of light is equal to wavelength times frequency. So wavelength and frequency are inversely related. When the wavelength is high, the frequency is low, and vice versa. And then energy is equal to Planck's constant times the frequency. So as the frequency increases, the amount of energy in the wavelength, in the light, also increases. And so the important thing to know here, or what Bohr used, was the fact that wavelength, the color of light that we can see, is related to the amount of energy that it contains. So we have two different types of spectra, a continuous spectrum. And so you guys have probably seen this, like when sunlight goes through some kind of prism, and then you create a rainbow. And when you create a rainbow with using sunlight, you usually see all the colors of the rainbow. So starting with red, and then going continuously all the way through violet with no gaps, no missing colors. So this would have every type of wavelength in it. It would also mean it has every type of energy light. This is different from when we have a hot gas. So we've seen in class a tube of hydrogen gas, which has been heated up, and it gives off light. And when it gives off light, it gives off just a few colors of light. It doesn't give off every single color, but just a few lines with a particular wavelength. And so if it has a particular wavelength, that means it must contain only a particular amount of energy and not every single amount of energy possible. Putting energy into an atom moves the electron away from the nucleus, from the ground state to an excited state. So again, with our Bohr model, here's your nucleus, and then here are your different energy levels or orbitals. And so if an electron is here at the ground state, and then we flip the switch and start to apply electricity or energy to it, it can move out to an excited state. So that takes energy. So putting energy in will move the electron out. And then the electron will only stay there for a fraction of a second. And then when the electron moves back down towards the nucleus from its excited state back to its ground state, then it's going to give off energy. And sometimes that's in the form of visible light. But it's giving off some kind of energy. And if that energy is corresponding with the wavelength that we can see, then we'll be able to perceive it as visible light. This is the emission spectrum from hydrogen. So hydrogen happens to have 4 different colors of light that's given off within the visible spectrum. And so there's a violet one with a wavelength of 410 nanometers, a blue one with 434 nanometers, a green with 486 nanometers, and one that's red with 658 nanometers. So why does it produce only these 4 colors of light and nothing else? So here's another picture of a hydrogen atom. So we have our nucleus here in the center, and then we have different orbitals where the electron can be found. And this equation right here is called the Rydberg equation. This is the Rydberg constant. And so this can be used to calculate the amount of energy that one of these electrons has at a particular energy level. So this is the first energy level, n equals 1, and then n equals 2, n equals 3, n equals 4, and so on. So as the radius increases, we're just going in integers away from the nucleus. And so let's say we wanted to do a problem where we wanted to find the amount of energy released when an electron moves from this 4th energy level down here to the 2nd energy level. So we have an electron that's been excited and is up here on the 4th energy level, the 4th orbital, and then it's going to move back down here to the 2nd, and we want to figure out what kind of light is it going to be giving off. All right, so what we're going to do first is at the 2nd energy level, let's calculate when n equals 2, how much energy does that electron possess? So to do that, we use the Rydberg equation. So negative 2.18 times 10 to the negative 18 joules over n squared. So when n is equal to 2, 2 squared. And so when you do this, you get negative 5.45 times 10 to the negative 19 joules. And then we'll do the same thing when n equals 4. So now we want to figure out how much energy this electron has. So energy is equal to negative 2.18 times 10 to the negative 18 joules. That's a constant again. And now n is different because we're looking at an energy level further from the nucleus, so 4 squared. And so when we do this calculation, negative 1.36 times 10 to the negative 19 joules. All right, and so now we want to figure out how much energy is released or absorbed when it moves from the fourth to the second. So we'll use this equation, delta E, the change in energy is equal to the final energy minus the initial energy. So delta E is equal to, well, it's going to end up here at the second energy level where it has negative 5.45 times 10 to the negative 19 joules minus the initial state was out here at the fourth energy level where it had negative 1.36 times 10 to the negative 19 joules. And so we take that difference and the change in energy is equal to negative 4.09 times 10 to the negative 19 joules. All right, well, let's take this a step further. So we have this amount of energy, and we know that each energy of light is related to a particular frequency. So if we take this amount of energy, this negative sign means that the energy is going to be released. Okay, so the negative sign, just like in our thermochemistry chapter, means that the energy is being released. When I use it in this equation, I'm going to change the sign to positive because I just want to, because I know the frequency has to be positive. So 4.09, the sign was just telling me the direction the energy was flowing out, times 10 to the negative 19 joules is equal to Planck's constant, 6.626 times 10 to negative 34 joules times seconds, and then times the frequency. So I'll solve for my frequency, and I get 6.17 times 10 to the 14th seconds to the minus 1. And then I'm going to use that to find the wavelength. So we know that C is equal to wavelength times frequency. So C is the constant for the speed of light, 3 times 10 to the 8th meters per second is equal to wavelength times frequency, 6.17 times 10 to the 14th seconds to the minus 1. And so we solve for the wavelength, and we get a wavelength of 4.86 times 10 to the negative 7th meters. We can change that to nanometers because visible light is typically understood in terms of nanometers. So if we convert that to nanometers, it's 486 nanometers. All right? And then if we see where we've seen that number before, let's flip back to our previous page. And this was the emission spectrum for hydrogen. So hydrogen had 4 colors of light being emitted, and one of them had a wavelength of 486 nanometers. So that 486 nanometers corresponds with an electron moving from the 4th energy level down to the 2nd. So we calculated how much energy it had at the 4th, how much energy it had at the 2nd. We took the difference between those two, and that amount of energy, energy can't be created or destroyed, so it has to be released as it moves from the 4th energy to the 2nd energy level. And that amount of energy corresponds with the wavelength of light, 486 nanometers, which we would perceive as being kind of a greenish color. So that was a calculation just for one of the transitions. This shows a lot of the other transitions that are possible within the hydrogen atom. So this shows the 1st, 2nd, 3rd, 4th, 5th, and 6th energy level, and then all the way up to infinity, or it's been completely removed from the atom. And it shows each of the transitions. So the one we looked at was from the fourth to the second. And so when it goes from the fourth to the second, it's 486 nanometers, and it corresponds with the green light. Other transitions with visible light, so from the third to the second, fourth to the second, fifth to the second, and sixth to the second, all give visible lights. These other transitions, so down here, anything going down to the first energy level is going to give, it still gives off energy, but it's not in a wavelength that we can see. It's going to give off energy in the ultraviolet spectrum. And then transitions that end in the third energy level are going to give off waves that are too large for us to see. They're going to be in the infrared region. So just to summarize a couple things about Bohr's model of the atom, only certain colors of light are released, and that's because only certain energies are allowed for the hydrogen atom. And energy in the atom is quantized. Electrons orbit the nucleus only at certain radii or certain energy levels. And this was the big contribution that Bohr made, was that the electrons can't be any distance from the nucleus, but only certain fixed distances. And so Bohr's model explains a lot about the atom. It's pretty useful, and we'll use that model frequently. We'll also find out in the next couple sections, that it's not perfect. There are some limitations to Bohr's model. We do have some theories that go beyond Bohr's model.